Hello everyone. Today we'll be solving the problem number 621, task scheduler. Right? So you can just go through the question and you can just try to understand the question with the help of examples that they have given. I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given a list of CPU tasks. You can clearly see here. We have been given a list of CPU tasks where each task is represented by the letter A to Z. So here you can clearly see where each task is represented by a letter A to Z and cooling interval N. So N is nothing but the cooling interval here. The CPU can execute only one task per interval. CPU can execute only one task per interval. So this we have to keep in mind. This is very important. The CPU can execute only one task per interval, but the same task cannot be executed again until n intervals have passed, since it's the last execution. Suppose here we are executing A, the second A should wait again until n intervals have passed, right? Since it's the last execution of A. That's what they have given in simple terms. If no task can be executed, then the CPU must remain idle. So if no task can be executed at a particular point of time, so the CPU must remain idle at that point of time. So what we need to do here, we need to determine the minimum number of CPU intervals required to complete all the tasks. So what we have to determine here, we need to determine the minimum number of CPU intervals, right, required to complete all the tasks that we need to determine. So they have given here AAA, triple B, here N they have given to output should be 8. Explanation they have clearly given here, a possible sequence A, B, idle, A, B, idle, A and B. So here we have to consider n plus 1, that we'll be discussing when we dry run the example accordingly with the approach. So output would be 8 here. Same goes with example 2 and example 3. So let's discuss the approach first, then let's dry run this example accordingly with the approach. Let's see whether the approach works or not. Then let's discuss the edge cases one by one, followed by writing the code and discuss the complexities of the code that we have written. Initially, let's discuss the approach and dry run this example, first example, right? So one thing we have to keep in mind here is we have to store the frequency of each task. How many times the task has been executed, that we have to store somewhere, right? The frequency of each task. For that, we'll be making use of hash map, and we have to make use of the maximum frequency tasks every time, right? So for that, we can make use of the max priority queue or the max heap. Let's go with the max priority queue because Leetcode provides built-in this one priority queue, right? If we want to make use of the max heap, we have to build the heap and then we have to perform the operation. So it is better to go with the max priority queue or the priority queue, right, in this case. So we are going with the max priority queue and the hash map for this particular problem. So first step, what we'll be doing here, we have to count the frequency of each task here. First, as we have discussed, we have to count the frequency of each task in this case. So this will be the first step. For this one, we'll be making use of the hash map. We will first for storing the frequency, we'll be making use of the hash map. Here we have to count the frequency of each task, right? We first count how often each task appears in the input, and then we will store that one in the max heap, max priority queue or the priority queue, since we always want to execute the most frequent task first. We always want to execute the most frequent task first. So this one we have to keep in mind. We always want to execute the most frequent task first. This is the first step. We'll be making use of max heap for that since the maximum value will always be at the root, we'll be making use of the max heap because we always want to execute the most frequent task first. So then we have to let's simulate the CPU execution. So here it's simulating, or let's simulate CPU execution. Exec I'll give here, right? So what we'll do here, well, the max heap is not empty. So when the max heap is not empty, we have to process up to n plus 1. This one we have to keep in mind. This is very important. So this is the approach that we'll be going with. This one we have to keep in mind. While the max heap is not empty, we have to process up to n plus 1 tasks at time. So n plus 1 tasks at time. While the max heap is not empty, we have to process n plus 1 tasks at time. Whether when n equals 2 they have given, we have to consider n plus 1 nothing but 3 tasks. So this is very important. Keep this in mind. While the max heap is not empty, we have to process up to n plus 1 tasks at a time. Then store the task temporarily in an array and decrement the count. This one, what we are doing here, we are storing the tasks temporarily in array, right? And finally decrement the count by 1 or decrement their count. In each step we'll be decrementing by 1. This one you will understand when we dry run the example accordingly with the approach, right? Now the third step here is, if the task still has occurrence left, push it back to the max heap. So if task still has the occurrences left, we have to push it back to the max heap. Then we will count the number of intervals needed to process the tasks in the cycle. So this is fine. This we have to keep in mind. The third step is handling the idle intervals. This one, handle idle intervals, right? When we do not have the task, we have to keep the CPU idle. So that's what they have given in the question as well, right? If there are still tasks remaining after the processing of a cycle, then we have to add n plus 1 tasks. This we know. If all the tasks are done in the last cycle itself, just count the actual number of tasks that are proceeded. So this is what the approach that we will be mainly going with. So first step is, in short, we are counting the frequency of each task. Then we are simulating CPU execution. Then finally we should be able to handle the idle intervals. This is the approach. So let's consider the first example that they have given in the this one question, and let's dry run the example accordingly with the approach that we have discussed now. So we have considered the first example that they have given in the question, right? This is the example they have showed. So the output that we need to get here is 8. N they have given 2, and tasks they have given A thrice and B thrice here. So we have task A that appears 3 times and task B that appears 3 times. So cooling time they have given here is N equals 2. So cooling time, nothing but here N equals 2, right? So task must wait 2 intervals before getting executed again. Here the cooling period is N equals 2 they have given. So task must wait 2 intervals before executing again, right? So let's try to understand this one step by step, right? Accordingly with the approach. So first thing is we have to count the frequency of tasks. Here A is 3, B is 3, right? So now we are pushing these counts into the max heap or max priority queue. Now max priority queue. Now we have 3 and 3. We have here. We have to count the frequency of tasks, right? Now in the priority queue we have 3 and 3, right? In the first step. Step 2, what we have discussed, we have to process tasks in cycles of n plus 1 intervals. We have to process the tasks in, sorry, just give me a second here. Yeah. step 2, what we saw in the approach, we have to process tasks in cycles of n plus 1 intervals, right? Here n they have given 2 here. In this case, n they have given 2. N plus 1 here, nothing but 2 plus 1 here. This will be 3, right? So let's go with the cycle 1 here. What happens in cycle 1 here? We have to uh, pick the two most frequent tasks. That is nothing but A and B are the two most frequent tasks here. We know that after executing them, reduce their count by 1. We have to reduce the count by 1. Since we only have two tasks, nothing but A and B, the third slot will be idle here. In this case, we'll go with A, B. Third slot is idle. Why the third slot is idle here? Because we have only two tasks, nothing but A and B. So we are reducing the count by 1 because now A has got executed once and the B has got executed once. So now in the cycle 1, remaining this one will be A will be 2 now, B will be 2. A was 3 times and B was 3 times, right? Since A and B got executed once, here you can clearly see, this will be remaining will be A to B 2. So now time elapsed here is time, I'll just give time here in this case. Time elapsed this 3, n plus 1 we are considering here 3. We are going with 3, right? This is for the cycle 1. Next, let's go with the cycle 2 here. So for the cycle 2, again we have to pick the two most frequency tasks. To pick the most frequent tasks, we have that is the reason we have made use of the priority queue. So again we have to pick the two most frequency tasks. In this case, we'll be picking A and B again. We only have A and B, right? So reduce their count and third slot should be again idle. We don't have any task. We have only two tasks, nothing but A and B. We don't have C, D, anything, right? We have only A and B. So here we'll reduce the count again because they get executed once and the third slot will be again idle. Here we'll go in this order, A, B, idle. This is fine. Remaining now will be same thing. A was 2 and B was 2 and now it gets executed once, so A will be of 1 and B will be of 1. And time elapsed here will be, last time it was 3 here, we saw n plus 1 was 3. This time again 3 plus 3, it will be 6 in this case. Time elapsed is 6 in this case. Let's move on with the cycle 3. So again we are now we have only A and B left, right? Now we have only A and B here. So A and B 3 times, we have the duplicates twice, right? For A and B 3 times it has the frequency of A is 3 and the frequency of B is 3. So we have executed twice and now only A and B are left here in the cycle 3, right? So both are executed and no more tasks remain here. The order will be A, B. So remaining, this gets executed, this gets executed here. Now remaining is none. So time, this time it will be 6 plus 2. Why 6 plus 2? Why we are not considering 3 here? Because this gets executed once. N plus 1 will be 1 plus 1. It will be this one, 6 plus 2, nothing but 8 in this case. So this is the output. Minimum CPU intervals that is required here is 8. So the output that we need to get here is 8 as well, right? So here what is the execution order that we went with? A, B, idle. This was first for the first cycle. Then again A, B, idle. This was for the second cycle, and for the third cycle it was only A, B, right? So 8 here. You can count here. 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So the output is 8 here. I hope the example that we have discussed now is completely clear. Now what we'll do, let's discuss the edge cases one by one and then finally write the code. Let's discuss the edge cases one by one. First edge case that we are going here is minimum input case. So just give me a second here. What happened here? This is fine. We are going with minimum input case. So suppose when I say minimum input case, let's go with tasks only one thing, A. One task, right? N, let me give here 0. Output will be 1, right? We have only one task here. So this is fine. Let's move on with the second edge case, nothing but all unique tasks. Here, when I say all unique tasks, so tasks, let me consider here A, B, C, let me consider D, and finally E here. This is fine. And N, let me consider here 3. So output will be 5 here. We can directly consider this one. Output will be 5. Why the output will be 5 here? Since no two tasks are repeating here, there will be no idling of the CPU. So the output will be 5 in this case. So this is for the second edge case. Let's move on with the third edge case. Nothing but high frequency tasks, right? High frequency tasks with large N. High frequency tasks with large N. So when I say this one, repetitive tasks has to be higher, right? So here in this case A, let me consider some 3 times here or thrice. So B, let me consider same thing. High frequency task we are considering, right? And C, let me consider here thrice as well. So here N, let's consider N equals 3. You can just visualize in the same way, or you can just try it out in the same way that I had shown for the example that they have given in the question earlier. We have discussed the same thing, right? We have dry run the example accordingly with the approach. So you can visualize or you can try it in the same way. So here the output will be 11 in this case for this one. High frequency task with large N, nothing but N we have considered here 3, right? So the output will be 11 for this. Let's move on with the fourth edge case, nothing but single task type with large N. Single task. Here, let's consider single task type with large N in this case. So tasks, let's consider here A. This one again, A 4 times. This is fine. And N, we have got 2 here. So the output will be 7 here in this case. Again, I'm telling you can visualize or you can try it out in the same way that I had shown for the example earlier. So here for this one, let me show the order here. This will be A, idle, because all the A's we have here, right? 4 A's we are considering here. So this will be A, idle, idle. Again, N equals 2 we have, right? So again, this will be idle. A, idle, idle. Finally, A, right? In this case, so the output will be 7. You can count 3, 4, 5, 6 and 7, right? So this is for the condition single task type with large N. First one was for the minimum input case. Second one was for this one, all unique tasks. Third one was for the high frequency tasks with large N, and fourth one was for single task type with large N. I hope all the edge cases are clear. So now let's start writing the code. I'll explain the code while we write the code itself and finally discuss the complexities of the code that we have written. So let's start writing the code here. As we had discussed in the approach, initially we'll be making use of the hash map to store the frequency of each task. So I'll just give here, let map, I'll just consider M here, new map. This is fine. So this is the first step. Then I'll just make use of the simple for loop here. I just consider individual task of tasks, right? So then we can just update using the set property of the map t, comma, to get the value I'll just be making use of map.get of individual tasks, or it can be 0 as well, right? If the tasks are not present, plus 1 we will give here. I hope this is clear. Next, we'll be making use of the built-in max priority queue for max frequency tasks here. So here what we have done, we have created a map to store the task frequencies. Now we have to initialize a max priority queue. So what we will be doing here, we have already created a map to store the task frequencies. Now we have to count the occurrences of each task and store in the map. In the example, if you consider, we have considered the frequency of A was 3 and frequency of B was 3 initially, right? So that's what we have to count the occurrences of each task and store in the map, right? So now let's initialize the max heap. I'll just give here pq equals new. We are considering max priority queue here. This is fine. Max priority queue. We are just initializing the max priority queue here. Next step is, let's go with the same thing. Let me make use of the for loop here. For let f of map dot values. Values we are considering, right? We'll be having key and values within the map. So we are just considering f of this one, values, map dot values we are considering. Then values, this is function, right? So this is fine. We are pushing the f, individual f. For that one, we'll be making use of the enqueue. As we are dealing with the queue, right? We'll be making use of enqueue. So this will be here f. This is fine. This is fine. So next step here is, let time equals, we have to initialize the time to 0 to keep the total time counter. So I'll just give here let time equals 0. This is fine. The next step, what we'll be doing, we have to continue the process while the tasks exist in the heap. So tasks has to exist in the heap to continue the process, right? So we'll just go with the simple while loop while priority queue is not empty. So there is a property called is empty, right, in the queue. So that we'll be making use of here. Is not empty, then what we will do, we have to let's make use of the temporary array to store the tasks that is processed in the particular cycle. So that's what we saw in the example. So I'll just give here temp equals empty array here. So next step is, let's process up to n plus 1 tasks per cycle. So how can we write that one? This we have already seen this one while discussing the example, right? So, or while discussing the approach. So here equals 0, I less than or equal to 1. So we are just articulating the approach in the form of code, right? So we can write in this way, simple if condition here. We are just removing the highest frequency task from the heap and we are decreasing the count in every in every cycle. We were decrementing the frequency by 1, or we were decrementing the count by 1, sorry, not the frequency, count by 1, if you remember. So that itself we are just articulating in the form of code here. When priority queue is empty here, this is fine. We were pushing here temp dot push pq dot dq. So we are making use of dq here dot element minus 1. I hope this is clear. So here if we dq is nothing but removing or deleting. Here accordingly with the example that we have considered, if we remove a, initially we were having the count 3, right? It becomes 2, right? And that is stored in the temporary variable. That's what we are doing here in this case, right? So we are just removing a, and so that the count and then we are reducing or decreasing its count. Suppose if we are having 3 A's, then we are removing 1 A and decrementing because A gets executed once and we are decrementing its count. Now the A will be 2. That's what we are doing in this step, if you remember this. So next step is we have to push the task back into the priority queue if still have if still they have the remaining counts, if they still have the remaining counts, right? So for that, I'll just consider for loop let t of temp still they have the remaining counts, then we are pushing tasks back into the priority queue. So here I can just write in this way: if t is greater than 0, task if still they exist, then we have to push back into the priority queue, right? So for pushing, I'll just make use of the enqueue. Here we have enqueue operation, so of t. This is fine. I hope this is completely clear. The final step is we have to add n+1 to total time if there are still tasks left, right? Otherwise, we are adding only the number of tasks that is processed in this cycle. I'll just give you a time plus pq dot size here. This is fine. This will be n+1. This will be length of the temp. I hope this is clear, right? This is fine. The final step is we have to return the total CPU time that is needed to execute all the tasks, or we have to return the minimum intervals that the CPU requires, right? So that's what we will do here. Just return time. We have considered time itself, right? If I remember, we have considered time itself. So here, yeah, we are just returning time here. This is fine. I'll just format the code once and let me hit the run button. So now you can clearly see the sample test cases are getting passed here. I hope this is completely clear. Now let me hit the submit button as the sample test cases are getting passed here. So here you can clearly see all the test cases are getting passed, right? So the code works absolutely correct. So now let's quickly discuss the time complexity and the space complexity of the code that we have written. So the approach that we went with here is, one is max heap along with the this one, what do we call, hash map, and the greedy, mainly greedy with the max heap we can call. We have made use of the hash map as well to store the frequency, but we can just call here greedy with the max heap or max priority queue, right? So overall time complexity would be here big O of n log n here in this case. So why here the time complexity would be big O of n log n, not the log n, because we are pushing or popping the elements from the heap that takes n log n times, right? So the overall time complexity here would be big O of n log n. So then what would be the space complexity here? The space complexity here would be big O of n. Why the space complexity here is big O of n? Because we are storing the task frequencies and using a max priority queue in this case. So overall space complexity would be here big O of 1. I hope this is clear. So the overall time complexity would be big O of n log n, and the overall space complexity would be big O of n, right? So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.